So our next speaker is gonna join remotely, and its name is Eugene Wu. And Eugene work is broadly focused on technology that help users to play with their data. His goal is for users at all technical levels to effectively and quickly make sense of their information. He's interested in solutions that ultimately improve the interface between users and data and use techniques borrowed from fields such as data management, systems, crowdsourcing, and visualization. Eugene received a PhD from MIT and was a postdoc at the AMP Lab. Eugene received the VLDB 2018 10 years test of award, best of conference citation from ICDE and VLDB. And then the NSF Career and the Google and Amazon Faculty Awards. Thank you very much for joining us, Eugene. You can get started with the presentation.
Hi, can you hear me?
Yes.
Okay, great. So thanks, everyone. What I wanted to talk to everyone about today is some of the research we've been doing on systems for human data interaction and kind of like what we're thinking about. And so to start, I like to contrast what we do with human-computer interfaces, right? So we know that HCI and human-computer interfaces is our kind of like window to computing. And one of the most powerful aspects to computing and technology is that it can empower people to build and create for themselves. And interfaces are clearly a key component of this. And I like to use kind of word processing as an example. So for millennia, scribes were basically the interface towards writing and copying and producing manuscripts, right? But today you can, open a web page and go to a word processor and write research papers, write novels, and write even local neighborhood announcements, and just create it on your own, right? Without any need for other help. And what's even more powerful than an individual word processing tool or interface is tools to help create new interfaces for other people. And over the last decade, what we've seen are these convergence of tools for creating new interactive applications and interfaces, right? And it's gone to the point where a non-programmer can create rich, beautiful, interactive, scalable applications without writing much code at all. And this is thanks to a combination of design tools like Figma and Plasmic and Webflow that are basically like Microsoft Word or kind of like Photoshop, but for interface and application design. Coupled with development tools that really simplify going from design to code. And these can be libraries like React and Vue and Svelte, but also these no-code libraries as well, like Airtable and Bubble. Right. And then the final kind of piece has been deployment, and effectively kind of deploying and hosting and running applications is now essentially free. So we all know all this, but of course, we also know that the center of gravity is shifting towards data-centric interfaces, right? And if we kind of look, the type of tooling and ecosystem doesn't exist at the same scale and kind of richness as it does for normal applications. Sure, we have large databases, we have data science applications and platforms like Jupyter, but the design tools, the coding environments, the one-click deployment doesn't really exist. And one of the arguments that I like to make has to do with scale in terms of the difference. And so we can compare a traditional interface like the one on the left. This is just like a spreadsheet or that's showing 10 rows from some database, right? As compared to a data interface, where in this case, this is a very, very simple bar chart, right? And so it's visualizing maybe statistics from 10 different rows. And if the data set is really just 10 rows, like they're essentially equivalent. There's no real difference. But as the data set scales in size, then the traditional interface is still showing 10 rows, right? It's not showing any more information. Whereas the data interface is now representing maybe 1 million records, 1 billion records, right? And it really, the amount of data that's summarized and represented in the data interface just scales and essentially unbounded. And this creates technical challenges that also affect design and creation as well. So one challenge that I just kind of mentioned is scale. But the other challenge is this notion of design dependence, where how you design a new application and interface directly affects the system architecture, and they're deeply coupled. So I wanted to start by just giving you a sense of what I mean by these two terms. In terms of scale, if your data set is very small and everything can just run in the browser, then we have very, very good solutions, and the problem is arguably solved. But you can imagine if your data set grows a little bit, then the architecture might require you to then run things on your laptop rather than just directly in the browser, right? And if the data set grows a little bit more, maybe it doesn't even run on the laptop and you need to allocate a server or a standalone database. And if it's even larger than that, then maybe you have to go to the cloud. Now, all of this introduces complexity and latency at these system boundaries, as well as network and communication overheads. And you're essentially running a distributed system, right? But the user, of course, doesn't really care because the interface hasn't changed and the user expectations are still the same. And so oftentimes applications now add caching in order to hide these latencies. And if the caches are quite smart and you want to query against them, then they start looking like databases smeared across the stack. And we have very, very good solutions for each individual problem in this kind of like large architecture. However, the core issue really isn't any individual issue, right, or problem. It's the fact that you're programming essentially against a memory hierarchy, right? And we know that programming against such a thing is one of the fundamental challenges of computer science. But in this case, what we're asking the designer to do is manually program against and optimize against this kind of architecture, this hierarchy, right? And this signals both a lack of good abstractions and the fact that this is a massive kind of like pain point and makes kind of creating new data interfaces brittle and challenging. Now, the other aspect, you might say, well, if I have like scalable databases, this is all solved. So like, why is this a problem? Well, the other is this notion of design dependence, right? And so what I want to show you here is an example where on the left, we just have a very simple interface that's just showing legislative votes for different chambers in Congress. And on the right side is a client server architecture with just different types of optimizations. And you can imagine that if the interface is just click two buttons to look at statistics from the 90s or 2000s, the optimization is very simple, right? You can just pre-compute the results for each decade. And when the user clicks on a button, then you can just send the pre-computed results over to the browser. That's done. But let's say the designer changes the interface a little bit, and now you want to use a range slider instead. Well, then now you have to pre-compute a quadratic number of views, right? Because that's how many potential kind of date combinations you have. But this is going to then require a different data structure, such as a data cube or some other data structure. And maybe you might also have optimizations like pushing this and caching in the browser and so on, right? And then maybe the designer decides to change things a little bit again, and then allow you to look at this information for different chambers as well. So each of these ends up requiring different combinations of optimizations and system design and system architecture decisions. And so this is a trivial example, right? And you can see that things can be a little bit complex. But you can imagine in any real application and interface, right, the fact that the interface design is coupled with how you're going to design and optimize the system makes things very, very, very painful. Right. And so the trend in most application development on web and on mobile is towards no code levels of simplicity. Yet this combination of scale and design dependence is making this harder than ever for creating data intensive interfaces. And so what we've been working on in our lab is to think about, and address three classes of problems and questions under kind of like this notion of how can we make tooling in this ecosystem easier and better. Right. And so at the foundation level at the bottom, we've been studying, well, what kinds of system primitives can we kind of develop and make easy to use to more easily express and build and automatically optimize, future human data interfaces. And above that, we've been also asking the question, well, how can we make it more easy to design new interfaces that are amenable to optimization, but also useful, right? And at the very top, if it becomes easy to actually design and create new interfaces, then what other capabilities can they have beyond just showing data and clicking on widgets? And so we have a variety of different projects at each of these different layers. But I just wanted to show really just two demos for a few of these projects. So the first one is related to some of the points made in the previous talks, which is around lineage and provenance. So I'll start with a system called Smoke. And the main idea, right, in the previous talks, we've talked about provenance in the sense of knowing what data tables were used or data sources were used to compute a result. But here, what we're going to look at is something a little bit more fine-grained, which is at the record level, how can you know which individual records were used to compute a given result? So for example, here, you don't have to look at this notation. What we're going to do is we're going to take these two tables and we want to join them, meaning join them on color or on ID. And then we might do something like an aggregation, right, on color. And so we know that this is kind of like the intermediate and final results. And what fine-grained lineage describes is the record level relationships in each of these steps, right? So what this means is if you look at the first output O1, well, we know that it depends on the first two join results. And we know that the first join result also depends on the first record in the top table and the first record in the bottom table, right? A1 and B1. And so this forms a graph that tells you for any input record, what output records it corresponded to and contributed to, and also for any given combination of output records, what inputs were used to compute them. And this is useful for a variety of scenarios. For example, debugging is one, but also privacy, right? For example, you might want to say, I don't want to release any query results that depend on private data or private records. It's been useful for distributed protocols and debugging them, incremental view maintenance, and a lot more, right? But the challenge traditionally with this is that it's also very, very expensive. This is why people don't really track this stuff. It's because it can lead to 10 to over 1,000x query slowdowns in order to track all of this information, right? And you can imagine that databases today, especially analytic databases, are heavily optimized for read queries. But now you're asking us to write all of this lineage information at the record level. So this can be very expensive. So for example, a traditional way that you might do this is to annotate every record that you're computing with some of its lineage information, right? So here, these gray cells correspond to the IDs of the input records that were used to generate them. And you can imagine then tracking them throughout this process. But this kind of thing makes things very, very slow for a bunch of different reasons. But the thing is, we would actually like to use lineage for a lot of these applications, yet a system doesn't really exist, right? And one of the motivating applications beyond security and debugging and privacy and all of these other things has actually been to use lineage as a way of expressing interactive applications and interfaces. And it's because it's a natural way of expressing interactions. For example, here, right, we have a data set and we've decided to render the data on the screen as a scatter plot. Now, when we point to data that's rendered in the screen, what we're really referring to is the actual input records that were used to compute these points, right? And this is precisely what backward lineage corresponds to. And if the data was then rendered in a different way, for example, in a bar chart, then we often, when we select points in one chart, then the other chart updates in correspondence, right? And this corresponds to forward lineage or view refresh. It's to say, I want to update everything else that's derived from this input data set, right, to reflect what I've selected and pointed to, right? And this is at the core of interaction. And so declaratively, what this means is I have kind of like these pixels, right, this kind of visualizations I'm looking at on the screen, and I want to then join them with my user interaction. In this case, it's a selection box. And I want to then compute the backward lineage to know what records were used to compute it, and then refresh something else, right? Refresh another view, for example. And so what this means is a lot of interactive applications can be expressed using this primitive, this lineage primitive. Right? For example, visualization you can model as a complex SQL query, and then interactions is lineage as well as more SQL on top of it. Right? And this is not only useful for just visualization, but also data is manipulated and rendered in many, many different forms. For example, Yifan and Arvind's WIST-20 work explored how you can reference lineage in code, right? For example, you might want to select points in a visualization and then use that as part of a query somewhere else, or to use it to fit a model. Now, all of this makes sense because what this is lineage is a correspondence between your input data and what you see on the screen. Right? Unfortunately, existing systems are very, very slow if you actually want to track and store this stuff. And so one of the things we've been pushing over the past several years in my group is to actually build engines that can efficiently materialize and track this information at the record level. And so you can imagine a database engine or kind of a data analytics engine, where as you execute each operator, what it's going to do is also track and generate these lineage indices that tell you, well, which input records in each operator correspond to which output records of those operators, right? And if you track all of this information during query execution, then if I point to anything in the output result, then I can figure out, well, by following this chain of relationships, what the input records were that corresponded to it. And so our early work, Smoke, showed that this was possible by building a custom engine. And what we've done recently is to actually extend this open source database engine called DuckDB to actually support this with very, very low overhead. And what I wanted to do is just show a demo of this in action, rather than kind of showing you performance graphs. And so I'm going to show a demo where we have 5 million records of kind of like this fires data set where this tracks kind of different forest fires around the country. And we're just going to render different attributes and then show cross filtering. And so what this means is I'm going to show different views of the same data set. And when I select some subset of bars in one chart, then what I want to do is basically filter for the subset that it corresponds to in the input database, and then update and re-aggregate the other views, right? And so traditionally, this is how you would implement it using SQL. And what I'm going to show is how to actually do this and how it accelerates and enables these interactions by using lineage, right? Because what this is actually doing under the covers is when you select a set of bars, we're going to use the lineage information that SmokeDuck tracks in order to figure out what subset of the input data it corresponds to, and then also use the same lineage indexes to try to figure out, well, how can we update the other charts? This is view refresh. So I'm going to show you a demo here. And this is basically using DuckDB. And so I've created these two bar charts, and what they are just aggregating over different attributes and showing you the histograms, right? And cross-filtering is essentially the interaction where you can select a subset of these bars, and then the other charts will change in correspondence, right? And what we can see here is that if you just do this using something like DuckDB, then it can take seconds in order to update, in order to reflect the updates in the other charts, right? And if you want to then create like another visualization, another chart, for example, for to aggregate over a year, then if we then perform these interactions, then things just continue to be very, very slow, right? And so it's easy to implement this kinds of visualization. However, it's very, very difficult to make it fast. And so what I wanted to show you here is an example of this using lineage. And so what we're going to show here is as we load these different charts, the system is dynamically generating and tracking this lineage information I've been talking about. And we're going to use it in order to actually support these interactions, right? And what we can see here is that as I perform these interactions, the query latency in order to update these other charts is in the single-digit milliseconds. And what this means is that lineage is actually being used to optimize these interactions. And what's nice about this is because we have this lineage information, we can also directly query against it as well. For example, here what I'm showing is I've written a query where I want to just count the number of records that I've selected in the input database, right? So the lineage corresponds to the input backward lineage of whatever I've selected in this particular chart. And so we can see here is that as I'm kind of selecting different bars, in this chart, I'm also able to dynamically query the lineage information and use it as part of another query, right? But you could similarly use it, as part of like an input to a machine learning model or any other analytics. So what this basically shows, and what hopefully this highlights, is that lineage itself is very useful for a variety of different applications. And one of our goals over the past several years is to make it practical to actually use. And the way to do that is to make the overhead of tracking this stuff very, very low. And so the current overhead that we see today in our benchmarks is between 1% to 5% slowdown of the queries in order to track the lineage as well as generate the normal query results. So we're very excited about this. And one of our plans is to release kind of like this engine as well as kind of like a library to be able to use this for building applications. So I'm not sure how much more time I have and whether or not I have time to show one more demo.
We have 1 minute left.
1 minute left.
Yep.
Okay. So I think that's then maybe I'll skip this. So the other kind of like application that we've been kind of thinking about is whether or not we can not just help people program interfaces, but directly synthesize end-to-end usable interactive applications directly from queries, right? And the main idea, and I'll just describe the motivation and then skip to the end. The motivation is that a lot of interface building and a lot of kind of like tools that we have today, right, are designed for a particular task. And so you think very hard, and you've designed a task up front, and then you create the interface, right? And then you give it to people in the real world and hope that however you design the system is suitable for whatever the analysis that the user actually has. But we know that that's not really the case, right? Everyone has like different analyses, and some might be very difficult to express because the analysis is very complicated, or the SQL queries are very, very complicated. And so if we kind of look at the tools today for creating new data interfaces, we can categorize them in terms of how expressive they are along the x-axis and how easy it is to create them using these tools, right? So for example, on the left side, tools like Metabase are visualization systems that allow you to create kind of visualizations that are essentially parameterized queries, meaning you can vary a parameter or two, right? And then systems like Tableau are very, very popular and make it easy to create dashboards as long as the operations that you're performing are data cube and group by aggregation operations, right? And so, if you fit into that regime, things are very, very easy to use, and there's really great tooling. But the moment you try to move a little bit towards the right to have more complex analysis tasks, then really you're in the realm of writing your own code or paying someone to kind of like do this work on your behalf. And so the big question and the project behind precision interfaces is whether or not we can take kind of examples of the analysis you want to be able to perform and directly synthesize like an analysis interface on your behalf, right? So can we automate the process of creating analysis systems for you? So I think I'll skip kind of like how we go about doing this in the idea and the demo. And just to say, a lot of what we're doing in our lab is to think about the discipline of data management as well as visualization and human data interaction, and think about how we can take ideas from both fields and then use it to both improve kind of how we build database systems, how we build kind of visualization systems, but also at the intersection, how we can enable other people to build these more easily. And so we've been looking kind of at the realms of both functionality in terms of system primitives, interface design, as well as what kinds of capabilities future interfaces can support. And so my email is, my website is eugenewu.net, and I'm happy to take any questions.
All right, thank you very much for the great talk. Maybe we want to take some questions from the audience. Is there someone? Right, I actually have a question. So at one point you were describing the lineage and the explosion that you get from different combinations. You started with the example from the 90s and 2000, then you expanded there. My point is more like, if we introduce an extra dimension there, because what you were talking about is just the number of configurations, and we talk more about the size of the data, right? Which role has which impact has the size of the data, and does sampling has a role in the work that you're doing?
So just so I understand your question, you're talking about kind of like the demo where we're kind of like interacting with different charts and so on, right?
Yeah, and also connected
Okay.
to the really beginning of the presentation, but yeah, it's the same.
Yeah, so you're asking like, what's the role of sampling? I mean, sampling is one of many possible optimizations that you can, that a developer or a designer can have in their toolbox, right? And I think one challenge that designers have today is that if they're really talking about scale, they need to understand all the different optimizations and how to apply them and when they're kind of applicable, right? Because sampling is not necessarily free, and it doesn't magically just make things better, right? Like it has its own set of constraints, and also affects kind of like the interface and the data being shown in the visualization itself. And so all of that needs to be taken into account. So sampling, has a role just as any other optimization, in a given optimization toolbox. Right. The thing that that probably makes sense moving forward is to see how we can decouple like optimization choices from interface design. And so a lot of what we're doing today is trying to figure out what primitives and what kind of like languages and abstractions to do this.
All right,
Big
makes
question.
sense. Is there any other question from the audience? Otherwise, we can thank our speaker once again. And thank you very much, Eugene.